And we're ready. So, last time we spoke about properties of derivatives and how they affect graphs. We spoke about increasing, decreasing, maximums, minimums, concavity. We are going to put all this towards further sketching, but before that, I need to tell you about asymptotes. And then we'll jump into the handout that I gave you last time. So, you should have that ready. Okay. So, what is an asymptote? This is a curve. That your graph approaches is the keyword, as the x or the y coordinate. Go to infinity. So that's an asymptote. So, for example, y equals tan inverse of x has an asymptote. It has two, in fact. It has a horizontal asymptote and another horizontal asymptote. So this graph you should know. So as you notice, as the x coordinate is going off to infinity, this graph is approaching the line y equals pi over 2. And as your x goes off to negative infinity, this graph is approaching the line minus pi over 2. Of course, infinity. We have things like y equals 1 over x. That looks like that. You notice that this has an asymptote on the x-axis itself is an asymptote. As your x is going off to infinity, your graph is approaching the x-axis. As your x is going off to negative infinity, your graph is approaching the x-axis. There's also an asymptote on the y-axis itself. As your y is going to infinity, the graph is approaching the y-axis. As your y is going to negative infinity, the graph is approaching the y-axis. You also have things like hyperbolas would behave this way. So these are examples of vertical and horizontal asymptotes, but they don't have to be. You can look at a graph like x squared minus y squared equals 1. And that pretty much looks like it's centered at 0, 0. Move 1 to the left and to the right. Move 1 up and down. Create a box. Draw lines going through that box, through the diagonal. That should go through the center. And a hyperbola is the guy that, well, this hyperbola will approach those lines as you go up to infinity. So the equation of this line, which is going to be y equals x, that is an asymptote to this graph. Notice that as your x is going off to infinity, your graph is approaching that. Y equals minus x is also an asymptote to this graph. So these graphs have asymptotes. So here we have the asymptotes. So here y equals pi over 2, y equals minus pi over 2 is an asymptote. Here x equals 0, y equals 0 is an asymptote. Here y equals x, y equals minus x. These are asymptotes. So that is a behavior of a graph that will show up every now and then. We need to know when it shows up, and we need to know how to deal with it, how to actually sketch it, figure out what it means, that sort of thing. As you can see, we can have asymptotes of all kinds. They don't have to be straight lines, even though all these examples I gave you are straight lines. But we're not going to care about all of them for what we want to do. So there are many kinds. There are as many kinds of asymptotes as there are curves. You can just draw a random curve and say, oh, I'm going to draw a graph that's an asymptote to this curve. We care about two of them, about two kinds. They are going to be linear, so these are asymptotes that looks like a straight line, and they are going to be of the horizontal and vertical variety. So I'm going to need you to be able to identify via calculations and graphing horizontal and vertical asymptotes. So let's take them one at a time. Let's deal with horizontal. Which I'll probably abbreviate HA. So I can't bother writing that out all the time. So f of x is a function. Consider these two limits. The limit as x approaches infinity of the function, and the limit as x approaches negative infinity of the function. Now it might seem like forever ago, but we did do limits in an extensive sense. There's going to be some changes to the way you think about limits in Calc 3, but for the most part, what I talked about limits is going to last you forever, and it's most of what you're going to need to know about limits. Unless you're a math major, then you're going to know a lot more about limits, but basic computational classes, you know everything you'll probably ever need to know about limits. It's like one little thing that in Calc 3 with it, you're going to be adding to that. So we know how to do limits very well, hopefully, by now. If either of these limits give a constant, so k, then y equals k is an HA of x. Find the limits as x approaches infinity and negative infinity. If you get a constant value going in either direction, then you have a horizontal asymptote, and y equals the value of that limit is going to be the equation of that asymptote. Y equals 1 over x. We know that the horizontal asymptote is the x-axis. Y equals 0. How would we figure that out? Well, if you took the limit as x approaches infinity of 1 over x, you will get 0. And if you take the limit as x approaches negative infinity of 1 over x, you will get 0. You look at y equals tan inverse. You take the limit as x approaches infinity of tan inverse. The answer is pi over 2. Therefore, y equals pi over 2 is going to be a horizontal asymptote. If you take a look at the limit as x approaches negative infinity of tan inverse, the answer is minus pi over 2, which means y equals minus pi over 2 is going to be the equation of a horizontal asymptote. So you take these into the limits. It is worth mentioning here, if you have a irrational function, remember I told you how to find infinite limits of rational functions. We had that shortcut, which basically looked at the highest power on the top and the bottom, and then we made conclusions based on that. So that's something that you can use to your advantage. You are going to realize that in that rule that I gave you, it didn't matter whether they were going to plus or minus infinity. For rational functions, Both limits will give the same answer. So that might be something to be aware of if you happen to be considering a rational function. For example, 1 over x is a rational function, a ratio of two polynomials. Then whether you go to plus infinity or minus infinity, you will get the same answer. So you probably don't have to check both of them. For other kinds of functions, though, the answer can change. So you'll probably want to actually go through and take both limits. But for rational functions, you'll always get the same answer. That's it for something else I can say about horizontal asymptotes. Just so that you are aware. It is not strange. So don't think of it as strange. You end up in this situation, is that strange? Am I doing something wrong? Don't worry about it, because I hear people ask that all the time. It is not strange to cross horizontal asymptotes. It's just not strange. So you can have a horizontal asymptote at that number. And in the finite sense, in the interim, your graph can move across that line all at once, but eventually, as you're going off to infinity, as long as it settles eventually, right? As long as there comes a point where it just keeps getting closer to that thing forever, that thing is called an asymptote. Now, you can cross that asymptote in the meantime. So don't think of it as strange as if you cross the horizontal asymptote. That's more than normal. It's not weird at all. If you want to know whether a function crosses the horizontal asymptote, then that's kind of easy. Let's say this is y equals k. All you have to do is set your function equal to k. Is there an input that makes the output k? And you just solve for it. So this is y equals k, and you want to ask, does f of x cross the horizontal asymptote? Then what you would do is set f of x equals k and see if any x works. If there's an x value that works, then yeah, it crosses the horizontal asymptote at this x value. If there's no x that works, then no, this one doesn't cross the horizontal asymptote. So it's not strange to cross the horizontal asymptote. Don't get too freaked out if you're drawing something and it looks like it's going across the horizontal asymptote. That's pretty much all you need to know about horizontal asymptotes in terms of actually calculating where they will occur. You just find those two limits. That's how you find a horizontal asymptote. Vertical asymptotes are a little bit trickier, but the kinds of questions that you will normally be asked on a test that I'm going to ask you on a test, or that you would get on like a final or something, those are very few situations that you have to worry about. So, vertical asymptotes. The line x equals a is a vertical asymptote. So here's how you'd identify when one would occur. By the definition, technically speaking, we're going to have another way to actually look at this. If, as we approach a, as x approaches a from the right of our function, it is infinite. Or, could be and or, the limit as x approaches a from the left of f of x is infinite. Okay. So that means you have some graph where there is a line A, where if you're approaching from the right side, it might shoot off to infinity, right? And if you're approaching from the left side, it might shoot down to negative infinity, right? It will just either increase very rapidly, never touching that line, just getting closer and closer to it, or it will decrease very rapidly. So this is what a vertical asymptote means. There is some finite point, right? Some number on the number line, so that when you approach that number line from one side or the other, it doesn't have to be from both sides. Your graph could be very normal on this side. But if you approach from one or the other side, it's going to shoot up to infinity or shoot down to negative infinity. Such a point is called a vertical asymptote. So pretty much what you would have to do is you would have to check when would the one-sided limits give you an infinite answer. Now in general, that might be a little bit daunting, but for us, usually, we are going to be wanting to grab things that are rational, or at least algebraic in some very nice sense. So, for rational functions, ratio of polynomials. I believe that's what we'll typically deal with. So, some x value where the thing will shoot off to infinity. That should kind of remind you of, well, if you touch that line, there's going to be a division by 0 or something like that. So we can't touch that line. We have to really avoid it, right? So that is for rational functions where we'll be focusing on where the denominator equals 0. A very important reminder, something to check. Notice, and the numerator is not 0. With greater or equal multiplicity. So let me try to tell you an example here. Of course, we already saw that 1 over x, for example, would be an example of where vertical asymptote hits. At x equals 0, we have vertical asymptotes. I already drew a sketch. This is like that, right? So a graph like this would have a vertical asymptote. This graph in particular is 1 over x minus 8. Right? So a graph like that, all I have to figure out, oh, where's the denominator 0? It's 0 at x equals 8. That's what that's going to look like. But it's very important that I check that, is there something in the numerator that's 0 at the same time? Because that can actually change things. And we've actually seen an example of this. Here's an example, no VA, even though. We looked at this graph a couple times. So it's 1 over x minus 1. Look at that graph. Now clearly the denominator equals 0 at x equals 1. Is there a vertical asymptote at x equals 1? The answer was no. We realized that this guy was actually just x plus 1 times x minus 1 over x minus 1. So as long as we were not at 1, this graph behaved exactly like y equals x plus 1. The picture for this looked like that. There was just a hole at 1. So whenever your numerator has the same factor as your denominator and can completely cancel the denominator, we have a hole as opposed to an asymptote. So in this case, we get quote unquote, that's a technical term here, a hole. Now, you can have the numerator being the same as the denominator, but it just can't outmatch it with powers. That's what the multiplicity is about. So another one is something like this. If I look at y equals x squared minus 1, and this is over x minus 1 squared, then that's going to hit a vertical asymptote. Why? Because even if I did this, there's still going to be a division by 0 occurring. I can't actually get rid of it, right? So I need to make sure that the numerator isn't 0 at the same time as the denominator with greater than or equal to multiplicity. If the denominator, if they're actually 0 at the same time, but the denominator has a higher multiplicity, there's a higher power on the denominator than the numerator, then the numerator can't fully correct a division by 0 at that single point. You'll kind of still just end up with so for us, basically that's how you find a vertical asymptote, because usually the graphs we're going to be looking at would be graphs like this, rational functions. Marks here. In this class, this is not general, but in this class, because we'll usually be looking at rational functions, it is strange to cross a vertical asymptote. If you draw a graph and you drew a line across the vertical asymptote, well, for sure, in a test that I would give you, for sure you're wrong. That's not going to happen. I'm not going to give you a question where that's going to happen. In your homework, they might give you some weird example where you can cross a vertical asymptote, but I'm never going to ask you something where you cross a vertical asymptote. So if you draw a picture and you cross a vertical asymptote, one, I would know that you're not paying attention in class and you didn't just hear what I just said, for one. And two, you're really not paying attention because the numbers aren't going to work out for you. You would have a division by 0 happen. So it is strange, right? Not that it can't happen. It can happen, but not for us. And by the way, when it does happen, it'll happen once, right? But not for us. How do you know it'll happen once? Because if you pass a vertical line 2 times, you're not a function anymore, right? You'd fail the vertical line test. So it's possible that you might cross over it 1 time, but no more. But for us, it's not going to happen. I'm not going to answer a question where it's going to cross the vertical asymptote. So pretty much figure out where the denominator is 0. Make sure nothing in the numerator completely cancels that thing. That's going to be where vertical asymptote is going to occur. If you take the limit as x approaches infinity, or the limit as x approaches minus infinity, and you get a constant number, that's where a horizontal asymptote will occur. We don't care about any other asymptotes. So if any other situation happens, we don't care. I won't expect you to identify that situation. So we'll identify these 2 situations. That being said, now let's actually jump into some examples. We are going to do curve sketching. Now, yes, this is definitely one of those things where I'm not going to use this in my life. True, yes, you're never going to have to sketch a curve in like real life, other than in calculus class. This is true. Although sometimes you're trying to figure out a problem, being able to do a quick sketch by hand is going to be very helpful. But in general, computers are much better than us at sketching curves. The reason why we still ask you to sketch curves in Calc 1 is because there are many nuances that deal with a derivative and its first and second derivative of a function. And curve sketching kind of tests whether you know what these things mean in a very nice, compact way. I can see by how you drew the picture that you understand what the second derivative did, right? It's just me checking that you understand the nuances of these different derivatives. So it's just going to be a nice way for us to pretty much test you. Do you know what a first derivative does? Do you know what a second derivative does? And so usually, there's going to be a problem on an exam, definitely on a final, where you're going to have to be sketching some sort of curve according to certain stipulations, and it's just to really test whether, do you know what a derivative would do to some function that you care about. So to that end, we are going to look at the curve sketching handout. And on the first page, there are some kind of instructions, just summarizing a bunch of things that we did where you're going to know what to do. And then on the second page, I also have a bunch of rookie mistakes, which I guess I'll talk about some of them as we're going through some examples. So if you made these mistakes, you're really not paying attention, don't make these mistakes. And here's some examples. I'll probably do one or two of these just for you to actually see how the processes work. But if I'm on a quiz or a test or something like that, chances are in the second set of examples what that problem is going to look like. So maybe let's just go with an easy example. Something that we all know how to sketch 1 over x squared, but we're now going to kind of do it in very higher detail than we normally do it. So let's do example 1. F of x equals 1 over x squared. Now, as you see here, a lot of things that I summarized about asymptotes just now, I actually put in a paragraph right here, so you can refer to that. Of course, eventually you're going to want to memorize this entire step. So basically, I gave you the steps here that will help you sketch any graph. There are 6 things you have to worry about. The first one tends to be the domain. You're going to want to know what points actually exist on your function. You're then probably going to want to find the intercepts and asymptotes, finding the x and y intercepts. Always a nice thing to do, finding the asymptotes. The way I show you is going to be important because you're going to want to know if your graph is avoiding some line. Then you're going to want to figure out where are your maximums, minimums, where you're increasing, where you're decreasing. We know that the first derivative helps us with that. Then you're going to want to find concavity. Where am I concave up? Where am I concave down? Are there any inflection points? You know the second derivative helps you with that. And then the last step is pretty much going to be sketch the graph, given all this information. And make sure the picture that you sketch falls in line with the information that you wrote down before. If you told me that there are 2 x-intercepts, and you draw a picture with 3 x-intercepts, why would you do that? You told me there were 2 x-intercepts. Why are you drawing the picture with 3 x-intercepts? Things like that will often occur. Students will just, I don't know, they do all this work and then they forget that they did it. So that's one of the rookie mistakes, by the way. I think I wrote that down somewhere. Because I see that all the time. Like, you told me there was like no x-intercept, but this graph crossed the x-axis like twice. What's going on? You're not paying attention. You're not paying attention to yourself. Right? You yourself just got an answer, and then you totally just ignored it. Like, yeah. Okay. So let's go through the motions here with 1 over x squared. So we're always going to do those 6 steps. I already have my talk here. So faced with this, the problem is you're going to say something like, oh, consider the graph f of x. Find all intercepts, asymptotes, where it's increasing, decreasing, where it's concave up, where it's concave down, points of inflection and domain. Use this information to sketch the graph. There's going to be like a whole paragraph that's going to ask you, find all this stuff, sketch the graph. Okay, so let's go through. We'll find one. The domain is what we'll find. What is the domain of this guy?
This can be 0.
Can be 0. How do you write that down?
X is all real numbers. I mean, X.
Interval notation usually.
Negative infinity to 0. Close. I mean, open bracket. Union. 0.
Right. Everything is at 0. So that's the domain. 2. We would find the intercepts. So, how do we find the x-intercepts? Set y equals 0, solve for x. No solution. How do you find the y-intercepts? Set x equals 0, solve for y. No solution. Can't do it. Okay. So right now I've identified this does not touch the x-axis, this does not touch the y-axis. I whatever picture I draw, it cannot touch either axis. There is no solution for the X or Y intercept. What's the third thing? Here I'm going to worry about asymptotes. One at a time. Let's find the horizontal. This means I'm going to take the limit as x approaches infinity of 1 over x squared. You can know that that's 0. The limit, notice that that is, whether I'm doing plus or minus infinity, that's going to be true. So I can just put plus or minus infinity instead of wasting time writing that down twice. Vertical asymptotes. Basically, denominator equals 0 when x equals 0. Right? And nothing cancels it. That is going to be a vertical asymptote. By the way, this means 0 is a constant, so y equals 0 is a horizontal asymptote. So I know there's a vertical asymptote at x equals 0, there's a horizontal asymptote at y equals 0. Those are the asymptotes. Now, the fourth thing I'm going to want to do, try to get some more space for this. Increasing, decreasing, max and min. How do I figure out where this is increasing, decreasing, or max, a max or min? First derivative. That's what the first derivative does. What is the first derivative of this? Minus 2 over x cubed. How do I find where it's increasing or decreasing, or max or min? Critical points, right? So the first thing you want to do, we did that last class. Wanted to find the local max or min, we found critical points. Critical points here. Huh? X equals 0, right? Critical points is when the derivative is 0 or undefined. This is a fraction where the numerator is minus 2. It's never going to be 0. So there's no solution for that. However, it is undefined when x equals 0, so x equals 0 is the only critical point. What we're going to do is we're going to draw a number line, we're going to put a 0 on it, we're going to test this in the first derivative. So I'm going to take a random point over here, like a minus 1, take a random point over here, like a 1, something easy. So I'm not going to pick 17.9, pick 1, it's easy for me to compute. I'm going to plug it into the first derivative. So if I take a negative 1 into the first derivative, what do I get? Positive or negative? Positive. I get a positive number, which means I'm increasing over here. If I plug in a positive 1 into that, what do I get? Negative, which means I'm decreasing over here. What does that mean about 0?
There's a maximum.
No, there is no maximum. Why?
Oh, these are just the slopes. These are just the slopes.
That's what the domain was for. Okay? 0 can be anything. 0 is not on your graph. So one thing to know, not a max. Right? Do not disregard anything that you've written before. It will all apply at the same time. 0 would be a maximum if 0 was on the graph. It's not on the graph. So it's not a max. 0 is not in the domain. Okay. So I know I'm increasing, I'm decreasing, but I don't have a maximum. So nothing really to test there. I would move on. Next thing I want to know, concave up. Where am I concave up? Where am I concave down? Are there any inflection points? Second derivative, exactly. So second derivative is is 6 over x to the fourth. Right? Just write these as power. So that I wrote as x to the minus 2. The derivative is minus 2x to the minus 3, which is this. And if I write this as minus 2 times x to the minus 3, the minus 3 comes down, makes it positive 6, and then I subtract 1 from the power, which gives me x to the minus 4. So I get 6x to the minus 4. So that is the second derivative. Now, critical points. X equals 0 is again the critical point. So that's 0, and I'm going to plug in numbers into the second derivative. However, it's easy for you to see here, hopefully, that that's always going to give me a positive number, right? So this is going to be positive, and that's going to be positive. And so what this means is concave up. So I'm shaped like a cup. concave up. I'm shaped like a cup. It does not mean increasing or decreasing. It means the shape of the graph is concave up like a cup. And that leads us to finally step 6, which I have to erase these 2 quotes. So you have this information written down. You need to remember what you graph must obey all that stuff. So step 6 is to actually graph. Found all the important features. Now we're actually going to put to paper and figure out what this thing is going to look like. So I would tend to write things down in this order. It always kind of works with me. I tend to want to plot points first. So the first thing I'd want to do is put in intercepts. In this case, there were none, so ignore that. I would put in asymptotes. Now, how do you put in asymptotes? So we had 2, vertical and horizontal. How you draw an asymptote is with a broken line. So write an asymptote at y equals 0. So I draw that. We also had an asymptote at x equals 0. So I put in my asymptotes. Next, I would kind of put in max and min, inflections, any coordinates there. We didn't have any. Oh, I forgot to actually write down the answers here. So here we have, for increasing, I would write we're increasing on minus infinity to 0. Decreasing, we're decreasing from 0 to infinity. Just write that below. Max, we have none. Min, we have none. So I actually write that under this. Over here, I know I'm concave up from negative infinity to 0. I'm also concave up from 0 to infinity. I'm not going to include 0 because it's not in the domain. And for inflection points, we have none, because inflections occur when we change concavity. So max, mins, inflections, I don't have any of those. Okay, so the next thing I'm going to put in is my intervals. Increasing, decreasing, and concavity. So here's how I like to write my intervals. Way at the bottom of the graph, I'm going to actually draw them in. So increasing, I'm increasing from 0 to negative infinity. So from here, going back, I just draw that down at the bottom and I write I and C to tell me, okay, in this region it's increasing. And decreasing from here forward, right, DEC. In this region it's decreasing. No max and min. Okay, so I go over here, concavity. Okay, so I'm concave up. From here all the way back, I'm concave up. And from here all the way forward, I am concave up. Okay, so pretty much everything that I got from the, and then finally, sketch the picture. That fits the above. So pretty much, I go to my graph and literally everything I calculated, I'm going to summarize it on the picture, right? So I never have to look back at the calculations and get lost. What am I looking at again? Everything, I go step by step, I summarize it on the picture. I draw in my vertical and horizontal asymptotes. I would put in my max and mins and all my inflections. I'd write in my intervals, all that good stuff. So now from looking at the picture, I know what I can actually draw. Now, there are a couple ways that you can get started. Especially here, we don't really have any points that we should pass through. So you can actually start plotting one random point just to get yourself started. Or you can actually just use this in the information that you had before. So I know I have to be increasing concave up, so I'm moving up looking like a smiley face. So now the question is, could I start here and move up and look like a smiley face? Why not? Because I would create an X-intercept. And I just said I didn't have any X-intercepts. So the graph can't be down here, it has to be up here, right? So even without me plotting a point, I will know where the location is. So I know I need to be going up as I move from left to right. That's what increasing means. I know I should be doing it looking like a smiley face. So I should be doing this. I can't touch this line, and as I go off to negative infinity, I should be getting close to that line. Therefore, it only makes sense that that's going to be what the graph is going to look like. Right? I couldn't start down here, had to start up here. I had to always be moving up and to the right. That's the picture that fits that behavior. It doesn't touch any axis, so there are no intercepts, and that's that. Then I do the same idea over here. I know I'm decreasing. Decreasing means I should be going down and to the left. I'm also concave up, so I know as I'm going down and to the left, I should shape like a smiley face. Concave up like a cup. I know I can't be down here because if I keep going down and to the left and then go over here, I would create an X-intercept. There are no X-intercepts. So the entire graph must be on top. And again, this is the only thing that it could look like. And yeah, we knew that was going to be the answer, but I just wanted to show you something that, you know what the picture should look like, so the calculations is what I really wanted to pay attention to. Yeah, so, I know, hell freezes over, you forget how to graph 1 over x squared, you could actually figure it out again from scratch. But that should never really happen. Maybe you in a parallel universe would forget, and then you should tell him about it. So that's it. So that's curve sketching. Pretty much I'm going to give you a problem. You're going to go through these 6 steps. And you're going to find all these things that I asked you to find, and then you're going to draw a picture to show all those things in action. Let's see. Should I do another one or just jump straight to it? Set y equals 0, solve for x. I don't know if I want to waste time. Maybe let's just do the other 3. I was going to start another topic too, but I think we'll just stick with curve sketching for now. We'll try to get through the bottom 3 examples. If there's time left over, then we'll do this. If not, we won't worry about it. You can try it on your own for extra practice. And of course, you can go to like Wolfram Alpha and type in the name of the graph and to check your answers there. But these ones are more like what you would see on a test, actually. So this is for you to get used to the process, but your actual testing conditions will be similar to this. So this will be one problem on a test or the final, just to do this curve sketching thing. The phrasing will be somewhat similar to this. Consider the given function. The formula for f prime and f double prime are given and need not be verified. So they'll give you the function, they will give you the derivatives. Why are we being so nice? Well, because earlier in that same test, we would have already tested that you know how to take a derivative, right? There's going to be a problem before that that says, hey, find a bunch of derivatives. So we're going to know by the time you get here whether or not you can find a derivative. This is not testing whether you can find a derivative, it's it's testing, do you know what that derivative means? Do you know what it does? Do you know how it affects the graph? Okay, so we're going to give you the function, and we'll give you the derivatives for free. It's just up to you to make sure you're using them wisely. Okay, so consider this function. The forms for the derivative and the second derivative are given. You don't need to verify them. Find all intercepts, asymptotes, relative extrema, intervals of increasing, decreasing, intervals of cavity, inflection points if they exist, and use the information to graph the function, right? So the phrasing is going to be pretty much like that all the time. And then it's going to be, boom, here's a function, here's the first and second derivative. Go through all of that, tell me all of that, and actually sketch the picture. So let's actually do that. So let's jump into example 2. Should get through a couple examples here, try to make sure that everyone's kind of see what we're doing. So here our fx is x squared over x squared. So you need to graph that function, okay? After finding all this stuff, okay? So what are we going to do? We're going to go through the 6 steps. Domain. What is a domain? All real numbers except for 2 and negative 2. How do we write that down? Negative infinity, negative 2, negative 2 to 2, and 2 to infinity. That's the domain. By the way, people, it's very common for students to forget the middle part. Don't forget the middle part. You avoid minus 2 and 2. Things between minus 2 and 2 will work. So don't forget the middle part. Okay, so that's the domain. 2, intercepts. X-intercept. Set y equals 0, solve for x. What do you get? Right, get x equals 0, right? The only time a fraction is 0 is when the numerator is 0, so the numerator is x squared. When x squared equals 0, the fraction is 0. Y-intercept. Well, this means you set x equals 0, solve for y. So your y is going to be 0 squared over 0 squared minus 4. So that means y equals 0 is your, these are your x and y intercepts respectively. Therefore, your x and y intercepts are the origin. 3, asymptotes. We only care about 2 asymptotes. We care about the horizontal ones. How do I find the horizontal ones? I find the limit as x goes to infinity of the function. What is that? 1. Right? Ratio of the highest, the x to the highest powers. That's going to be x squared over x squared. It's 1. You will actually get the same thing whether you go to plus or minus. So y equals 1 is an HA. Still get vertical asymptotes. Where are those? When denominator equals 0, it means x equals plus or minus 2. Let's write them separately. X equals 2, x equals minus 2. Notice that at those points, there's nothing in the numerator that can cancel that. If the numerator is 2, plug in 2 or minus 2, it's not going to be equal to 0, so it's not going to actually do anything. So those are the vertical asymptotes. Now the fourth thing we want to do is, it's already right here, increasing, decreasing, maximum, and minimum. What do we use here? Use the first derivative. And luckily for us, they gave us the first derivative. We are told that the first derivative is minus 8x over x squared minus 4 squared. So yes, you could find that using the quotient rule, and if you simplify, you would get that. Now, how do I do this? All right, going to say it equal to 0 or undefined. Where is it 0? When x equals 0. Where is it undefined? X equals plus or minus 2. These are your critical points. So I'm going to draw a number line, and I'm going to put all those critical points on this line. and I am going to test points in between them. -3, -1, 1, 3. And I'm going to plug into the first derivative. Now, you should be able to use the properties of the function to your advantage. Remember, you don't care about the actual value, you only care about whether it's positive or negative. Here, what you would notice is that the denominator is a square. Therefore, if the denominator is not 0, it will always give you a positive number. So in terms of signs, I can completely ignore the denominator, just forget about it. Plug in a -3 here, I will get a positive, positive, negative, negative. So that is the signs there. Do we have any maxes or mins? 0. Here I'm increasing, then decreasing. Here I'm increasing and increasing, that's nothing. Here I'm decreasing and decreasing, that's nothing. Here I'm increasing and decreasing, 0. Is 0 on my graph? Yes, 0 works. Okay, so that is a maximum. How do I know what the coordinate of the maximum is? Plug in 0 where? Into the original. Okay, so here is the derivative. I plug these numbers into the derivative to figure out increasing or decreasing. If I want to find location, the coordinate where this thing happens, I go to the original. That's what the original is for. So the coordinate, the max, is going to occur at the origin. So now I can actually summarize this section. I can talk about increasing, decreasing. I can talk about maximum, minimum. So where are we increasing? From -infinity to -2, union from -2 to 0. Where am I decreasing? Well, from 0 to 2, union from 2 to infinity. Where is my max? My max occurs at the coordinate 0, 0. Where is my min? There is none. So that is the answer for this section. Now, I wanted to talk about concavity inflections. Well, what do? Second derivative is what I care about, and lucky for us, they gave us the second derivative. The second derivative is 8 times 3x squared plus 4 over x squared minus 4 cubed. We want to set this equal to 0 or undefined. That's what we care about. 0, no solution for that. The numerator is never 0. It's 3x squared plus 4. So it's going to be 4 or bigger, and then you're multiplying that by 8. So it's never 0. It is undefined when x is plus or minus 2, though, so those are the guys I care about here, and I'm going to test in the second derivative. I'm going to plug in random points, -3, 0 is nice enough here, 3 over here. Again, I'm going to use the function to my advantage. Notice that the numerator is always positive, so I don't care. Only care about the denominator. Plug in -3 here, I would get a positive. Plug in a 0 here, I would get a negative. Plug in a positive 3 here, I would get a positive. What does positive mean here? Concave up like a cup. You're positive, you're smiling, you're happy. Negative, concave down like a frown. You're feeling negative, you're down. And positive. Do you have any inflection points? Where? Right. This would be an inflection point. I did switch from a positive concavity to a negative one, but -2 is not in our domain, so that's nothing. Same goes for 2. I switched from negative to positive, but 2 is not in our domain, so that's nothing. There is no inflection. So here we have concavity. It's concave up on -infinity to -2, union 2 to infinity. It is concave down between -2 and 2. As for inflection points, there are none. So, let's see what this graph looks like. Hopefully you have this already. I'm going to erase this, remember what it is, so you can remind me what it is. So, I'm going to go over here, I'm going to X, Y, and I'm going to put in all the important features first. So, intercepts, the origin, there was only one intercept. In fact, that was a maximum also. So the intercept was a max, so let me just write that on the graph so I know, okay, that should be the highest point in that local region. Okay. Asymptotes. Y equals,
Y equals.
so there's a horizontal one, y equals 1.
And vertical at 2 and negative.
Vertical at -2 and 2. You guys know the guy from MIT Open Courseware that can draw the dotted lines really quickly? You guys ever seen that? It was like, he's like dotted lines all over. No, doesn't it? Yeah, never mind. I'll figure it out one day. One day I'll figure it out. I don't know how to do it. It's like, it sounds like a machine gun going on. I don't know. Anyway, okay, so those are the asymptotes, vertical and horizontal. Remember, I can't touch the vertical ones. I can potentially touch the horizontal ones, but we'll worry about that later. No inflections, we already have the max. But now I can put in increasing and decreasing. So here I know I am increasing here. I am also increasing between here. I am decreasing here. And I am decreasing going all the way over there. In terms of concavity, from here back, I am concave up. In the middle, all the way up to here, I am concave down. And from here, all the way forward, I am concave up. So those aren't on the graph. You draw them light or faint because you might not have multiple colors. So now we can actually start to draw the graph. Now the middle part is somewhat obvious. I know I have to be passing through this point, and if I'm increasing, it means I should be going up and to the right, so it will have to go down like that. I know I'm concave down like a frown. I know I can't touch the vertical asymptote, so that's going to be that. Over here I should be decreasing. I'm still concave down, so I'm shaped like a frown while I'm decreasing. Go like that. So that part's okay. What about on the outsides though?
On the left side,
Yeah, that's left side.
it's increasing.
Can I be here?
Yeah. It's part of the domain.
No, I mean specifically where my fist is. Can I? The answer is no. Why not?
Because you're going to have to cross through the...
Because this says I'm increasing, which means I'd have to cross the x-axis, which means I had two x-intercepts, not the one I found before. So my gap isn't down here. Question, is it up here, between here and here?
You can't touch the white.
How do you know it can't touch that? Because in general, you can touch the horizontal. So now you might ask the question, to check if it's here, you might check, is f of x equal to 1 anywhere? So that means you have x squared over x squared minus 4. Is that equal to 1? Well, if I multiply both sides by x squared minus 4, that means that 0 is equal to -4. So, no, that's crazy. That can't happen. So I don't cross this. So I know I'm not here. I must be up here, right? So there were 3 potential regions. I know I'm in this one, right? Because I can't cross this and I can't cross that, and I need to be increasing. So now I know I'm increasing concave up. So very similar to the 1 over x squared graph, it has to look like this. So I'm approaching this as I go up to infinity because that's a horizontal asymptote. I'm approaching that as x approaches -2 because that's a vertical asymptote. So that's what the left side looks like. Now you go over to the right side. Can I be down here? No, because I should be going down like that, and I would cross the x. Can I be right here? No, because I should be going down like that, and I would cross this, and I know I don't cross that. So I know I'm totally up here again. For the same reason, I know I'm moving down and to the right. I also know that I'm shaped like a smiley face while doing this. So that's the graph. So a 3-part graph looks like that. And probably in pre-calc, we didn't care too much about how you drew the curves per se. I mean, you don't have to be an expert artist, but you should be bending your curves in the right way, right? So as long as you don't bend that way, like, it's gonna be fine. So make sure you're bending the curves the right way. You shape like a smiley face when you should shape like a smiley face. Shape like a frowning face when you should shape like a frowning face. Let's try the next one. Let's try D. Any questions on this before we move on? So these would be, as you can probably guess, it's going to be one of the longer type problems. But the saving grace is it's pretty predictable in the sense that you always do the same things in the same order. And you'll get the derivatives. So it's just going to be a bunch of calculations and then coming up with a picture. It'll take you a while to get through it, but if you know what you're doing, you should get through it okay. So on a test, budget 10 minutes for this. 15 minutes if you're really slow, and make sure you average it out so that you get enough time for the other questions. But yeah, 10-15 minutes should be what you're spending on one of these. So when you're studying at home, practicing your homework, be sure to, not necessarily homework, but when you're studying for the test, be sure to time yourselves. You want to get through a graphing problem, a full problem in about 10 minutes, 10 to 15 minutes. Let's do it again. Okay, first thing, domain. What's the domain? All real numbers. 2 intercepts. What's the X-intercept?
0.
X equals 0. What is the Y-intercept? Also 0. Asymptotes. So that's the third thing you're going to do. Horizontal. How do you find it? Limit x approaches infinity of the function, which is 0. Plus or minus will approach the same thing. So y equals 0 is the horizontal asymptote. Look at for the vertical asymptote.
There are none.
None. Denominator is never 0. Next thing you're going to do, increasing, decreasing, max, min. You can leave this template up here. So, what do I need for the increasing and decreasing? Well, the first derivative, of course. So we're going to do f prime. So, we need the critical points. What are those here? Plus 1, negative 1. Denominator is never 0. So, negative 1, plus 1. I'm going to plug in random numbers. So, let me plug in, say, 0, minus 2, and a 2. And I'm going to plug those into the first derivative. Denominator, always positive. So let me look at the numerator. If I plug in a 2 here, I get 1 minus 4, which is negative. If I plug in a 0, I get a positive. And if I plug in a 2, I get a negative. So I am decreasing, I'm increasing, again, and decreasing. Do I have any maxes or mins? Negative 1 is what?
Negative 1 is minimum.
It's a minimum. And you'll see that 1 is a maximum. So now I am going to plug these, write these in. So increasing, I am increasing on minus 1 to 1. Decreasing, I am decreasing on negative infinity to minus 1 union 1 to infinity. Maximum, this is 1 comma, how do I find the y? Plug it into the original. So that's going to be 4 times 1 over 1 squared plus 1. That's 4 divided by 2, so that's 2. Go to the original to find the coordinate. Minimum, minus 1 minus 2. Right, because you're just putting minus 1 here. The denominator will still give you positive 2, but the numerator is going to be negative 4. So you have that. What? So those are that's the situation for increasing, decreasing, max, and min. For concavity, I am going to care about the second derivative. Which here that is given as ax times x squared minus 3 over x squared plus 1 cubed. Critical points. 0, radical 3, and minus radical 3. I'm going to plot those on a number line, testing the second derivative. Negative radical 3, 0, radical 3. And I'm going to plug in numbers between them, say a minus 2, a minus 1, a 1, a 2. The denominator is always positive again, so I just worry about the numerator. Plug in a negative 2. This is negative times positive. It's negative. Plug in a minus 1. This is negative times negative, so positive. Plug in 1. This is positive times negative, so negative. Plug in a 2. This is positive, that's positive, this is positive. So I'm concave down, concave up, concave down, concave up. Inflections?
Isn't that all the focal points?
Yeah, we have three of them. Inflection, that's an inflection, and that's an inflection. How do I know it's an inflection? Because I changed the concavity. Here's it from negative to positive, there's it from positive to negative, there's it from negative to positive, and these points are actually in my domain. So they are inflections. So now, I can write that down, concave up. Well, from negative radical 3 to 0, union radical 3 to infinity, concave down, negative infinity to negative radical 3, union 0 to radical 3, inflection points. Well, there's one at minus radical 3, comma something, comma, there's one at 0, comma 0, comma, there's one at positive radical 3, something. How do I find that coordinate? Well, it's a location. For location, I go to the original graph. I'm going to plug in negative radical 3 here, so I have minus 4 radical 3. Plug in negative radical 3 here, that's going to be 3 plus 1, which is 4. The 4s are going to cancel, so I'm going to have minus radical 3. And with a positive radical 3, I'm just going to get the positive version of this answer. So positive. So notice here there are commas here, not unions, because they're not intervals. It's a list of points. Yeah, so that brings us there. Now we are ready to sketch the graph. At least I'm ready. Are you ready? Let's go. So, starts out the same way. Drawing our axes. X and Y. First thing we're going to put in is our intercepts. What are our intercepts? The origin was an intercept. By the way, the origin is also an inflection point. So let me write that in, inflection. Okay, so I just had those intercepts. Asymptotes. With the horizontal one, right? So y equals 0. It's horizontal. We didn't have a vertical. Other coordinates, maxes and mins. Well, we had a max at 1, comma 2. Just call this. Let's call this 1, and let's call that 2. And we had a minimum at minus 1, comma minus 2. Okay, what else do we have? We have inflection points at radical 3, radical 3. Radical 3 is what, 1.7-ish? Here, it's going to be an inflection point here. Also inflection. This is at radical 3. Radical 3. We also had an inflection at minus radical 3. Minus radical 3. Label that inflection. This was a max, you label that. This was a min, you label that. So I'm summarizing all my calculations on this picture. The intervals increasing. I am increasing between here and here. And I'm decreasing outside of those windows. Concavity. So between 0 and minus radical 3, I am concave up. And from minus radical 3 to negative infinity, I am concave down. Between radical 3 and infinity is here. Concave up. And in the remainder, I am concave down. That's everyone. You just drew everything I know is now on this page, which means I should be passing through these points and with this behavior. So this is kind of going to look not to scale here. I'm kind of seeing what the graph is looking like. That might be a little messy. Okay, so the minimum and maximum, we kind of know that that has to look like that. Okay, so let's see. I only touch the x-axis once. So starting from the left, if I'm decreasing, I can't be decreasing from above the x-axis. I have to be decreasing from below the x-axis. And I know this is a horizontal asymptote. So off to negative infinity, I'm definitely beside the x-axis. And I'm decreasing concave down, decreasing like a frown. Right? So I'm bending this way while I'm decreasing. Now, something happens when I hit this point. An inflection point happens, which means I'm going to switch my concavity. I'm going to switch from a frowny face to a smiley face. However, I'm still in the decreasing region. So I'm still decreasing, but now I switched how I'm decreasing. So that happens. Okay? Starting at this location. Now, once I hit this point, from this region onwards, I'm going to be increasing. I'm going to be increasing in this entire space right here. However, in this region, I am increasing concave up, so I'm increasing looking like a smiley face. While in this region, I'm increasing concave down. I'm increasing looking like a frowny face. So here, I'm increasing like a smiley face, but I hit this point, and then I continue to increase, but I look like a frowny face. So that happens. Now I'm coming over to this region. Between these 2 points, I am decreasing concave down. So I'm decreasing looking like a frowny face until I hit that point. Now I'm at that point, and now I don't care about this region. I'm decreasing, but now I'm concave up. I also know that I'm not going to touch the x-axis because the only x-intercept is there. And I also know that this is a horizontal asymptote, so it makes sense that this goes like that. And that's the graph. Should be symmetric. I'm getting bored, so we'll stop there. Do the last one on your own. I might start next class with that one and then go into the topic that I actually want to talk about. So yeah, part C, x squared minus 9 divided by x minus 1 all squared. Sketch the graph.
No inflections.
Come again? Next week about what?
Wednesday? On Monday?
Yeah, Monday.
Is it quiz?
Oh, you asked quiz? No, no quiz. I think after Thanksgiving we have a quiz.
Should be long.
Is it gonna be like everything that we've been doing?
Yes, I'll give you more information. And since I already made some printouts, I'll just hand those out too. So on Monday, I want to talk about a new topic called optimization. And those are word problems, so I'm not going to be writing those questions out on the board. Yeah, so we'll stop there. So bring these with you next time because that's what we're going to be using. You can read through it ahead of time if you want, maybe even try a few problems so you can get it. And we'll pick up on Monday.